Welcome everyone, my name is Alex Alvarado and I'm with the Information and Communication Theory Lab at the TU Eindhoven in the Netherlands. Welcome to my presentation about constellation shaping for the nonlinear fiber optical channel. The motivation for this work is, as you see up here, an SNR gap. If you look at the achievable information rates versus SNR for a Gaussian channel and you increase the constellation size for QAM constellations from 16 to 64 to 256 and so on, you will see that there is a gap of 1.53 dB with respect to the capacity of the channel. This gap is called the ultimate shaping gain and can be closed using geometrical or probabilistic shaping, signal shaping. What's exciting about this is that if you have a non-Gaussian channel, as we do because we have the nonlinear Schrödinger equation or the Manankov equation, the gains that you could achieve are could in principle be larger than 1.53 dB. Two possibilities to approach the capacity of the channel. Essentially, one is probabilistic shaping, which is changing the probabilities of the symbols, not using equally likely symbols, but change the probabilities. And option two is geometric shaping, which means that instead of using square constellations, you're going to be using geometrically shaped constellations where you move the constellation points in 2, 4, or 8 dimensions, for example. And I will be talking about these two approaches in this presentation. So let's start with geometric shaping. I'm going to be talking about achievable information rates versus SNR. And the way you need to understand achievable information rates is as transmission rates, as ultimate rates that you can achieve based on what information theory tells you. We're going to be looking at mutual information and generalized mutual information. Generalized mutual information is the one that we must pay most attention to, and essentially that's the pragmatic approach. And think of soft decision LDPC code. So that's what is relevant. That's what GMI is relevant for. What you see here is that for a Gaussian channel, you can do 16 points, blue curves, 64 red, and 256 green. And you can optimize the constellations based on GMI or MI. What you see here at the top left is the optimization for mutual information, and what you see at the bottom right is the optimization for generalized mutual information. You see two things here. One is that the geometry of this optimization, the geometry of this optimized constellation is not exactly the same because the cost function is different. And you also see that the optimal constellation depends on the SNR that you're targeting. The gains that you can obtain vary between 0.2 to 0.4, 0.5 dB. And it comes by, you obtain these gains by essentially moving your constellation points around in your transmitter and using that constellation as the receiver in your DMapper. So what are the gains in the nonlinear optical channel? What we did is to pick these constellations, light blue, for example, that you see up there, green and red, and we use them in nonlinear fiber optical simulator. If you look at the solid lines, the curves on the right, black solid is 64 QAM, and the colorful dots, light blue, green, and red, shows you how much you can gain in terms of reach by using this geometrically optimized constellation. It could be up to 300 or 400 kilometers, depending on what rate you're targeting. Okay. Now, what happens if you want to design formats for the nonlinear optical channel? Well, we came up with this idea of using polarization ring switching, PRS, and we proposed a new format, 4-dimensional format with 64 symbols. And we designed this by maximizing linear performance, GMI, and also by minimizing the nonlinear tolerance. The way we did it is essentially to look at constellation points in 4 dimensions. What you see here is the projection on the X polarization and the projection on the Y polarization. And in each polarization, you have 2 rings. And the nice thing about the format, the design, is that if you, in the X polarization, transmit one of the points in the inner ring, that would be blue or red, you're forced to transmit a point in the outer ring in the second polarization, and the other way around as well. And this means that the energy, the modulus of these constellation points is actually constant. And this is what you see in the Stokes space. So by doing constant modulation and by optimizing the GMI, we actually managed to get very nice results. We compare this against two formats with the same spectral efficiency, polarization multiplexed 8QAM, and 6 bits, 6-bit Constellation proposed by Mitsubishi a few years ago. So that's state-of-the-art format. And yeah, we looked at the performance both in the Gaussian channel, and this is what you see here. You have the capacity and you have the baseline. That's polarization multiplexed 8QAM. And the two solid lines are the mutual information results. So both formats, Mitsubishi and our format, actually give pretty good results. If you look at the GMI, the pragmatic rate, you see that the state-of-the-art format actually loses quite a bit, while ours, which is the red dash curve, actually maintains more or less the gain. So that's a very nice result. In terms of gains, we depending on what you look at, 0.4 to 0.7 dB gains. We also looked at the performance end-to-end. So this is post-LDPC bit error rate for 20% overhead and also for 25% overhead. What you see here is that for both 20% and 25% overhead, the results that are predicted by the achievable information rates are maintained. Essentially, we get 0.4 or 0.45 or 0.46 dB gain with respect to state-of-the-art in end-to-end simulation for the Gaussian channel. Now, we also did this in an experiment. Experimental setup is rather standard, 42 gigabaud signals in a 50 gigahertz spacing, 11 WDM channels, dual polarization, standard single mode fiber. And we looked at the prefect bit error rate, which is what you see here on the left curves, and post-FEC bit error rate, which you see at the bottom right. And in both cases, both prefect bit error rate and post-FEC bit error rate, what you see is essentially a gain of 16 to 17% in terms of reach, which means that by using this constant modulus 4D 64 PRS, you can gain about 15, 16, even 17% reach increase in terms of transmission, right? So that's the experimental demonstration. There are two obvious questions here. Can we optimize this? Can we go even further? And there are two obvious possibilities here. Extension number one is to go from 6 bits to 7 bits, and extension number two is to go from 4D formats to 8D formats. We have actually done both of them. What you see here is the design that we did for 7 bits per 4D symbol. And what you see on the right is the numerical results. The format that we proposed is essentially a generalization of what we did for 6 bits, but we introduced the idea of Orthant-Symmetry because the optimization becomes very, very difficult very quickly. So we added this constraint to be able to solve the optimization problem, but the end result is a format that is, that gives you gains in the order of 900 kilometers. When compared to a modulation format, in this case set partitioned 16 QAM with the same spectral efficiency, you get gains of about 900 kilometers. So this is by going from 6 bits to 7 bits. And the second generalization is to go to 8 dimensions. We did this by looking at 2 time slots and using our 64 PRS format in 2 consecutive time slots. And we had parity, one parity bit to essentially connect these two connect these 2 time slots. And we proposed 2 formats, type 1 and type 2. Type 1 is good for high SNR, and type 2 is good for medium SNR. And the overall result is a truly a-dimensional format with 5.5 bits per 4D symbol. The results in terms of effective SNR is what you see up here. And you see that the green and the red, which are type 1 and type 2, these are our formats, when compared to a 5.5 bit state-of-the-art format in 4D, the effective SNR is higher, right? And that means that you have nonlinear tolerance. So we do achieve nonlinear tolerance with this 8-dimensional format. And what you see here is a result of the experimental demonstration, right? Essentially, the red curve is the baseline, polarization multiplexed 8 QAM, while the green is the time hybrid approach, which gives you 5.5 bits per 4D symbol as well. What we see here is that the blue curve is good for medium distances, so that is high SNR, that's expected, so that's type 1 format, and the type 2, which is the orange one, is very good for, it's the best for very long distances. Overall, the gains that we observed here are in the order of 5% reach increase with respect to state of the art. So that's about geometric shaping. Now let's go into probabilistic shaping, which is the second alternative to close this SNR gap. So what you see here is uniform signaling, 64 QAM, where you essentially concatenate a systematic FEC code with 64 QAM transmitted through the optical channel, and then do all the inverse processes at the receiver. To achieve non-equally likely symbols, you can use the probabilistic amplitude shaping, the past architecture approach, where you essentially add an outer layer, which is this amplitude shaper. And this works in this reverse concatenation, in the sense that the FEC becomes an inner code and the shaper becomes an outer code. Nice thing about this is that you achieve great adaptivity by changing the rate of this outer layer, which is the most important part in the architecture, right? So I will be discussing two possibilities, ESS and CCDM, on how to implement this amplitude shaper and amplitude deshaper. CCDM, the kind of standard approach to do this, is constant composition distribution matching. What you do is that you have a sequence, you have a set of amplitudes, A1, A2, A3, and so on, and you want to generate a sequence of length n, S1, S2, all the way to Sn. For constant composition, you fix a composition that you want to target, and then you make sure that every sequence that you generate actually satisfies this composition. By doing this, you can target a distribution, Gaussian-like, for example, and you make sure that all sequences actually have equal energy because they all have the same composition. Now, geometrically speaking, this means that all the sequences that you generate with constant composition distribution matching are on an n-dimensional shell because they all have the same energy. The alternative is ESS, which is the one that we have been investigating mostly at TUE, and that's enumerative sphere shaping, where you, instead of looking at matching distributions, you put an energy constraint, and you say we're going to transmit all sequences that satisfy this energy constraint. Everything that is below this energy can be transmitted. Now, you do not match in principle a distribution, although if n tends to infinity, the induced distribution is Gaussian, so that's a nice approach, but you do not in principle match distributions. Geometrically, what happens is that instead of transmitting sequences on a shell, you actually transmit all sequences within an n-dimensional sphere. So let's look at an example. Suppose that you do CCDM with composition 4-1. You have two possible amplitudes, 1 and 3, and block length is 5. You have 32 possible sequences from 1, 1, 1, 1, 1 to 3, 3, 3, 3, 3, right? So CCDM will pick 5 sequences, and out of those 5 sequences, you're actually going to get 4 of those, the dark red ones here. And that's because you want to transmit 2 bits of information. The average energy is 13 because they all have the same energy, 13. And geometrically, it means that you're transmitting the sequences on the second shell. Now, if you do the same for ESS, you put an energy constraint, 21 in this case, you come up with 6 possible sequences, green sequences that you see there, and you pick 4 of those to get the 2 bits that you're interested in. Geometrically, you get the innermost shell and a bit of the outermost, the second shell. And in terms of energy, you end up with an energy of 11, which is smaller than 13, which means that ESS is more energy efficient than CCDM. Okay? Now I'm going to show you a comparison between ESS and CCDM. I'll be doing this in terms of achievable information rates. What you see here is the GMI, which is the quantity that I've already showed you in the first part, but this is a definition. It's the mutual information between the bits that go into the mapper and the symbol output. And what you see on the right is the generalization of the GMI to the case when you have non-uniform signaling. That gives you what is called the BMD rate. but I'm also adding a term which is a rate loss. Combined, this gives you a finite block length achievable information rate. And that is something that we want to have because we're interested in comparing systems for finite block lengths. And that means that you want to subtract a loss that has to do with the finite block lengths regime. This rate loss is something that goes to 0 when n tends to infinity. This is good, and it's a fixed number for a fixed finite block length n. Okay. Now, in terms of performance for the linear channel, you see here the capacity of the channel. We're looking at a finite block length achievable information rate versus SNR. Uniform signaling is the baseline. If you do CCDM with block length 200, you get certain gains. If you do CCDM 3600, much longer block length, you get larger gains. Now, what's exciting and interesting here is that if you look at the performance of ESS with a much shorter block length, 200, you more or less match the performance of CCDM 3600. So you can more or less achieve the same gains with a much shorter block length. So that's exciting. So why is this? Well, the answer is on the figure here on the right, and that's rate loss. So the rate loss for CCDM for a finite block length is much higher than the rate loss for ESS. So that's one way of seeing it. The other way of seeing this gain is by looking at the geometry of the sequences that you generate. So ESS generates sequences within a sphere, while CCDM generates sequences on a shell. So essentially ESS is able to enumerate more sequences. Okay, this is why ESS is better than CCDM for finite block length. Asymptotically, they all converge, but for finite block lengths, ESS is better than CCDM. We tried to test this experimentally, more or less the same setup that we had before, and we're comparing uniform signaling with these three shaping schemes. We changed the FEC rate here at the bottom right, you see that in the table, to make sure that you get in all cases the same net data rate of 9 bits per 4D symbol. Performance is finite block lengths versus finite block length achievable information rate versus total launch power. That's the result for uniform. If you do CCDM 200, the performance goes up. If you do CCDM 3600, it goes even higher. And again, ESS 200, much shorter block lengths, more or less matches the performance of long block length CCDM. Gains are in the order of 0.2 bits per 4D, and all the way on the right you see also that ESS seems to have a slightly better nonlinear tolerance. In terms of transmission reach, essentially the same thing. You gain by doing CCDM 200, you gain even more by doing CCDM 3600, and ESS 200 more or less matches it. And 14%, 15% reach increase, which is also something that you can that we have looked at in terms of end-to-end experimental results. So this is post-shaping bit error rate, information bits in all the way to information bits out. You also see 15% reach increase. Now, two more things to conclude. The first one is why is this happening for probabilistic shaping? So if you look at this figure, you see achievable information rates versus shaping block length. For the dashed lines, this is the linear channel, and you see that as you increase the block length, the achievable information rate goes up and up and up, which comes from the fact that the rate loss tends to 0 as the block length tends to infinity. This is completely expected. But if you look at the curves for example, ESS for the nonlinear channel, that would be the solid blue curve, you see that as you increase the block length, the achievable information rate goes up, it reaches a maximum, and then it goes down. This means that there is an optimal finite block length, which is 400 to 400, and that comes from the fact that both CCDM and ESS, when you decrease your block length, the effective SNR actually goes up. What we have observed is that for short block length probabilistic shaping, the effective SNR goes up. So there is a balance between this effective SNR going up and at the same time the rate loss going up. This balance means that there is an optimum finite block length for probabilistic shaping based on ESS, and that's quite interesting. And the last one, and with this I conclude, is the question that I always get: should we do geometric or should we do probabilistic shaping? I'll try to answer that with these results. We recently compared the performance of our 4D Orthant-Symmetric format with probabilistic shaping at the same net data rate. Probabilistic shaping, those are the green curves, and that's for 32, 64, and 128. That's the block length increasing. And you see in the first figure that, as I said before, when you look at probabilistic shaping, you see that when you increase the block length, actually the effective SNR goes down, right? And you also see that our format, more or less, in terms of effective SNR, the geometrically shaped format is more or less the same as short block length probabilistic shaping. In the middle, you see finite block length achieved information rates, and you see here that essentially geometrically shaped format is approximately the same as probabilistic shaping with 64 amplitude. So that's the block length. And what you see in the figure all the way to the right is that if you're going to do probabilistic shaping with a short block length, say 32, that will be the dotted grid line, you actually can do better if you do geometric shaping. However, if you're willing to invest block lengths of 64 or 128, for example, you actually outperform probabilistic shaping, outperforms our geometric shaping. Okay? To conclude, a few remarks. First one is that signal shaping is a very exciting topic. It allows you to increase reach and data rates. You can do geometric shaping, you can do probabilistic shaping. And if we look into the future, I think there are at least two exciting topics to work on. One is to fully understand why this block length dependency, the SNR dependency on the block length for probabilistic shaping. And we also want to understand what happens if you go from 8 to, for example, 16 dimensions in geometrically shaped constellations. Okay, I would like to conclude by thanking you all for listening. I'd like to acknowledge the funding agencies that support our work at the ICT Lab, and also to thank all my collaborators and co-authors. We've been working on this for a few years, and this is just a snapshot of all the things that we have done. Thank you very much.